Hey folks, so today I want to talk about a system design for an ad click aggregator. Now, before I get started, I want to add a disclaimer that the walkthrough I'll be doing through is inspired by this particular article and the corresponding video. I have been using Hello Interview to brush up my system design skills as well as data structure skills. So, this particular system design would be inspired by this particular article. Cool. So with that in place, let's get started. Now, before we start with the system design, the first question is what exactly is an ad click aggregator? So the idea is that websites like, let's say, Instagram, Facebook, or any other portal which serves ads needs a way to first of all track those ads, and secondly it also needs a way to allow the advertisers to figure out, to query the metrics based on those ads, who clicked at what time, and so on and so forth. So this particular system design talks about that. That's the problem statement. Now let's go ahead and talk about the functional requirements for this system design. So the first functional requirement would be when a user clicks on an ad, he or she should be redirected to the ad and the click should be logged. So redirect the user to the corresponding URL when they click on an ad and log the click. So that is point number one. The other point is that we should allow the advertisers to be able to query the metrics. So we should allow the advertisers to query the metrics. Yeah, allow the ad to query click metrics. And the important thing here is that we should allow them to query at a granular minute level granularity. Okay, so minute level granularity. What that means is that they should be able to understand if an ad was clicked in the past 1 minute or let's say past 5 minutes. They should be able to figure it out. So the most basic unit is a minute. Granularity. Okay. Cool. Now there are some out of scope requirements, out of scope functional requirements as well. One, we do not talk about how we are going to place the ads. So ad placing or targeting. And the second part, so this was from the user perspective, and from an advertiser perspective, we are not going to support querying based on, let's say, demography or region or geography. So advanced query based on region or demography. Cool. So these are our functional requirements. Now let's move on to non-functional requirements. So the first is low latency. From the query perspective. So low latency query. So this means that when an advertiser queries the database, he or she should be able to get the query data as soon as possible. Let's say 1 second. So let's say within 1 second. Now the second thing is scalability. So let's say our system will have 10k clicks per second, and we have, let's say, 1 million active ads. The third is fault tolerance, that is availability. System should not go down. System should be highly available. Fourth could be we do not lose any click data, as well as the data integrity should be maintained. So capture, rather not click data plus data integrity. Now what does data integrity mean? What that means is, let's say, one of the use cases is that if a user clicks on an ad multiple times in, let's say, a couple of seconds, within 2 seconds he or she clicks 5 to 6 times, all those clicks should be captured as only one click, not 5 or 6 clicks. This is one way to think about it. The other way is any system, any wrong push, anything which could tamper with our data should be taken care of. So we need to make sure that the data which we are capturing and providing to our advertisers is picture perfect. Fifth thing is real-time analytics. So as a user, as an advertiser, I should be able to check the performance of my ad in real time, how it was responding, what was the performance, let's say 2 minutes back, 1 minute back, 5 minutes back. And the last could be let's say data idempotency. So data idempotency actually was the multiple click thing I talked about. And data integrity is like the data should be we should not be calculating wrong metrics. Okay, now there are some out of scope functional requirement, non-functional requirements here as well. One, we do not talk about let's say fraud detection. So for example, there's a bot which comes to our website and clicks a particular ad at every 30 seconds or every 10-15 seconds. So we're not going to handle that. Second would be let's say we will have a CI/CD pipeline. Cool, I think that is it. Now with the requirements out of place, let's talk about the system interface and data flow. Now ideally in a more product-facing product-facing system design, like design in Uber or Book My Show or Dropbox, anything which are more user-facing, we will have a set of APIs. We will have set of API here as well, but this is a bit different from that perspective. So I'll be talking about first the system interface, what is going to be the input of the system, what is going to be the output, and then we'll also talk about the data flow, how is the data going to flow in a system. So let's talk about system interface. It's very simple. Input is user clicks and output is queried data. Okay, so that is the system interface, and then the last step before we delve into system design is data flow. The first is user clicks on an ad, redirect the user to the website and log the click. Third is the logging हो चुका, okay, ठीक है. So the advertiser queries click data. Yeah, cool. So this is it. With this we can get started with our system design. First we'll talk about the high level design, where we ensure that the functional requirements are set, and once that is done, then we will delve into the non-functional requirements. Okay, cool. So let's get started. The first thing we have is user browser. This talks to AWS API gateway, which does a couple of things for us like authentication, load balancing, etc. We do not need to go into detail about it. Yeah. Okay. There will be other things, but that's fine. The first thing this user does is it needs an ad. Whenever I open, let's say Facebook, any particular page, I will see an ad. How do I get that ad? So there will be ad service. So this will be a get call. So let me just get ads, and then this will talk to the ad service, The ad service will in turn talk to another service, another database rather, which is your ad database. Let's talk about. So by the way, we are not going to go into details about it, but just so we have our ad DB here, and then these two talk. So ad DB will have, let's say, an ad table which will have ID, which will have URL, rather redirect URL. It will have advertiser ID. It will have image, what to show. It will have text, what should be the display, and then there would be other metadata. This is good. So this ad DB has all the information about all the different ads we want to have, and so now the ad is served to the user browser, and then the user clicks on an ad. So there is a click event. And once there's a click event, this is what we want to talk about. So we have a click service, and we need to log this particular ad. So before we log the ad, before we log the ad, we want to redirect the user to the ad website. Now there are two ways to do this. One, we give the redirection URL at the same time when we give the ad to the user. So this would be get ads. Yeah, this would be a click event. Yeah, so I was saying that when we retrieve the ad from the ad database, at the same time we send the redirect URL, and this can work. The only problem with this approach is that some advanced users, super users, can bypass this particular route, which is they might right click on the ad, go on click copy link URL, and then they can open in a different tab without while our click service is not being invoked. That is wrong behavior. We do not want to do that. The other way we can do that, the other way we can redirect the user is through, we do not give the ad URL, redirect URL in this flow, but when a user clicks on this particular ad, we do two things. One, we request the ad URL, get redirect URL from our ad database, and then we give it back to the user. The user could be redirected, could be given a response 301 redirect, and we will redirect to the user. We will redirect the user in a new tab. The other thing this call will do is it will write to the click database. So this is our click database. We write to this database, and yeah, so with this particular flow, the first part of system functional requirement is done, which is redirect the user to corresponding URL and log the click. Okay, now this is done. So the click database will have few fields, which is again ID, ad ID. It will have user ID. It will have timestamp. What else it will have? And it will have other metadata, which is, let's say, what was the demography of the user, in which area did they do they live, region, which browser they are using, and so on and so forth. We are not going to talk about it because that is out of scope, but so yeah, this is the case. Now the other thing is this has to be a write optimized database, because we are going to have around 10K clicks per second. So we cannot have a normal, let's say, Postgres or SQL kind of database. A SQL kind of database which is write optimized might work, but for this particular use case, let's think about event store database like, let's say, Cassandra or DynamoDB. I'm going to use Cassandra here. Okay, so the first part is done. We have logged the users, the click, and now it's turned to allow the advertiser to query the data. The most simple way to do this is having, um, so this is our advert browser. What we can have is we can have a query service which queries the data from our AdDB, ClickDB rather, and it does a specific query which I will write in a while, just 1 second. Yeah, so we can have a query which is something like, say, select count star as total clicks, count star, not star, distinct users from click db where add id equals to this and time greater than t1 and time greater than t2. So okay, by the way, it will have timestamp. Yes, it has timestamp. And then ultimately we group by add id. Yeah. So if you look at this particular query, this is a fairly heavy query. We'll have to aggregate the data in real time and then we give back to the user. There are a couple of problems with this. One, the database which we are using is write optimized, not read optimized. So this will be a bottleneck. The other thing is there is a case where there are two cases, by the way. One, the first case is where because you're using the same database, it is possible that there might be a race round condition. We are writing from this particular loop as well as we are reading, so there might be a delay in this particular thing in the query which are being fetched. The other thing is there is no separation of concern. This particular database is doing both the things, read and write. So if in the worst case scenario, or because of whatever reason, this particular system goes down, then we will not be able to either read or either write. Both the things would be jeopardized. We don't want to do that. In the worst case scenario, we should have a different database which will support our read operations as well. So the problem of Cassandra could have been solved by the problem of only a write only database could have been solved by using a different database, let's say like DynamoDB or whatever. But because we also want to separate the users, the flows, we will introduce a different database which is read optimized database, and also allows us to read aggregated data, to have pre-aggregated data, so that whenever an advertiser queries the data, we should be able to give him or her the pre-aggregated data. Now how do we do that? So we have ClickDB here. What we will do is we will get rid of this particular query. We will have another service which is your Apache Spark. Now Apache Spark is a distributed So Apache Spark is a distributed parallelized operation which will query data from our Cassandra DB in, let's say, every X number of minutes, and then it will run a job which will map reduce all the data in parallel. It will run across multiple nodes, and after aggregating the data, it will upload the data on an OLAP database. OLAP database online analytics processing database, which is read optimized. And it also stores time-based data. So we can aggregate the data in real time there. I mean, obviously it is aggregated, but it is aggregated at, it's a minute level. So from T1 to T2, T2 to T3. But if we want to query data from T1 to T5, then it would be easier to do such kind of aggregation in real time through this OLAP database. So we will have OLAP database here. Our Spark will write to OLAP database. It will read from the Click database. And how will the Spark job run? It will be done by through a cron job. So let's assume that this cron job runs every 5 minutes, and every 5 minutes Apache Spark job runs. It collects the data from past 5 minutes, whatever the interval that might be. It aggregates data and it will put into OLAP database, which is, let's say, Redshift in our case, though it could be BigQuery as well. It could be your Snowflake as well. And this thing would look like clicks. So it will have add ID, total clicks. It will have timestamp or timestamp name into minute. Let's it be timestamp in time. Yeah, and then total clicks. Okay, metadata. Cool. So this almost serves our functionality. The only problem is that, so we are doing this at minute level granularity, that is for every minute we are running this job, and with this our functional requirements are met. Now we can move on to our non-functional requirements, and the thing I want to talk about first is this fifth one, the real-time analytics. So the problem with this approach is that we want the user to be able to query data of let's say past 1 minute, but our Apache Spark job runs every 5 minutes. Now it is possible that we schedule this cron job to run, let's say, every 30 seconds or 60 seconds or whatever, and it can solve our problem. But the caveat here is that the Apache Spark job takes its own sweet time to initiate. It's a heavy job. So even if we start every 30 minutes, 30 seconds, it will take some time to boot up. So that is the first lag we're going to have. Secondly, because multiple Spark jobs might be running in the same time, there might be a chance of overlap as well. So we want to take care of this particular situation. And how do we do this is we can have a data stream somewhere here. So whenever a user clicks, we put that data on the stream. And then at the end of the stream, we will have a stream aggregator, data aggregator, which will then write to our database. So let's get ahead with that. So I will remove this Click database for now. We will remove this Spark. We will remove this cron job. This is gone. This is gone. The OLAP database is here. And let me just move this here. So now what is happening is we have data stream, which could be a queue, let's say it is Apache Kafka or Kinesis queue, AWS Kinesis. Cool. Let's use AWS Kinesis, which is streaming queue. And then at the end of this, we have an aggregator, which is, let's say, Apache Flink. Now this Apache Flink writes to our OLAP database, And yeah, with this it is almost real time. This will happen in real time. Apart the stream will keep coming in, and we will be aggregating it in real time. um, there are a couple of things here. One, we can configure when the data should be aggregated, so the job could run, let's say, after every 1 minute or whatever. And to make it real time, there is a feature in Apache Flink known as flushing. So in the earlier case, if you are going to support 1 minute granularity, it could be assumed that the aggregation job would run after every 60 seconds, starting from 00 to 59. But we can also enable Apache Flink to dump the data, to flush the data after every 10 seconds. So from 0 to 10, we'll have some number of clicks, they are dumped. Then from 10 to 20, the additional number of clicks could be dumped and added to that particular table, that row. And in that way, we can have as real time as possible to the user. In the front end, this could be handled by, let's say, a dotted arrow. So the graph is like this, and then for the current minute, it will start from here, somewhere below, and then every 10 seconds it will keep on rising, and then at the end of 6 seconds we will flush the data completely. We will make a commit, and then we will move on to the next 10-second window flushing. Cool. So this becomes as real time as possible. Cool. And what else we could have done here? So this particular guy, advertiser browser, will keep on polling. We can also use something like WebSocket, but we do not need it here because, so this will, let me just add that thing here. Polls the OLAP or click, aggregated click rather. Yeah. So we will not have a complicated solution, let's say like WebSockets or server-side events. Primary reason is that they are a bit heavy. We need to have multiple other configurations in place, and most importantly, we do not need a two-way communication. We just want to poll the we just need a periodic ping on the server and retrieve the latest data. So from that perspective, we are not going to use a complicated solution like WebSockets or server-side events. We'll use the very simple solution of polls. Cool. So real-time analytics is done. Now let's talk about scale. We have 10 clicks per second. Okay. So a lot of this is already handled by, nothing is handled. Let's talk about it. So there are 1, 2, 3, 4 different places, other 5 different places where the system could fail. It could not support the X number of simultaneous request. And the most easiest way to do this is horizontal scaling. Almost all the cloud providers provide this system, the solution where you can scale a system horizontally depending upon the load, and that's what we are going to do here. So we will have horizontal scale on the click service, which is this one. Let me add one more. Okay, so this is scaled. Similarly, our databases could also scale like this. We can just add more nodes and this should work. By the way, when we are talking about these nodes, we need to talk about sharding, and I'll come to that in a while, because if we have multiple nodes, we need to make sure that we are not going to mess up with the queries. They should be going from the same place. Okay, so let's talk about this OLAP database sharding first. So this database should be sharded on the advertiser ID. So I, as an advertiser, let's say, have 5 different ads running in parallel. Now I can query all those ads on the individual IDs as well, which makes sense. But I might also want to see the performance of all 5 ads in parallel and see which is the most successful ad, so as to say, and then maybe remove the 2 most or the 2 least successful ads. So in that particular case, sharding based on the advertiser ID would be more prudent approach here as compared to sharding on ad IDs. So horizontal scaling, sharding on advertiser ID. Cool. So this is done, and then let's talk about these two services as well. Both Kinesis and Apache Flink could be horizontally scaled as well, and the way to do that is scale to shard on the ad IDs, so that, let's say, just 1 second. So we have to okay, cool, sounds good. Now we are sharding these. Yeah, so if close up this video. Cool. So if a user, if n number of users are clicking on x number of on x nodes, on x ads of the same ad, they should go to the same node, and that is about scale. The other thing here is that the capacity of the streams is also limited. So something like, let's say, Apache Kafka or AWS Kinesis only support X number of events, records per second, or X amount of data. So it is possible that you are able to put only one record on the stream because the data size is too huge, or the data size is small. Collectively, it does not reach the threshold, but the number of overall events are only X events supported. So the limit for Kinesis, if I remember correctly, is 1000 records per second, and then it supports 1 MB per shard. So from this perspective as well, we need to shard the stream as well as the aggregator. Apache Flink. This is our event aggregator. Okay, so far so good. Cool. Now, one important thing to talk about here is, let's say, the case of a hot shard. What that means is, let's say, a very popular ad comes in which is being hit by all the users. So what that means is that one particular shard, which is let's say during IPL season, ad by Virat Kohli is being hit by everyone. So that one particular shard will get overpopulated. The way to handle this is we can have multiple shards, and for that one particular ad ID itself. And how to do that is by appending a random number at the end of that ID. So let's say let's talk about hot shard problem. We have, let's say, an ID, which is the shard key, and then we append it by random number between, let's say, 1 to 5. So instead of supporting 1000 clicks per second, now we are supporting 5000 clicks per second. So that is one point. This way now we have 5 different shards for the same ad ID, and then they could be handled properly. But what happens at the aggregator level? How will it figure out that these are different shards? These different shards correspond to the same ad ID. So Flink again allows us to a configuration where one particular node can take data from X number of different shards. So we can configure Flink in that way that 5 different shards are being aggregated at the same time. So this could be taken care of. Now with this, our scalability problem is also solved. Now, with respect to low latency queries, if you look at this, we have already solved this. We will have this is aggregated data, right? So let me just write somewhere here. So the problem is already solved. The one place where this problem could still persist is if the user, the advertiser, wants to query data at a bigger interval. So right now we are supporting only at a granular level of 1 minute. But what if, let's say, the user, the advertiser, wants to query data at an hour level or 12-hour level, multiple days level? Now, if that is the case, then what we can do is we can run another job, aggregator job, which will put data, aggregate data over this number of hours in a different table, and then whenever the user, the advertiser, hits our URL, our query service for that duration, for let's say 1 day or 5 days, then we can query data from that particular table again, which has aggregated data over X number of days, and then we can serve that back to the user. So the low latency search is also solved by this particular use case, by this particular approach. Cool. Now let's talk about fault tolerance. Fault tolerance means that system should be available. Yeah, in any use case, the system, the nodes go down, system should work, and actually, if you think about it, that also has been taken care of. All these things, AWS Kinesis, Apache Flink, they are already redundant, they are parallel distributed, the data resides on multiple nodes by default. So in that situation, it is already fault tolerant. So the system is highly available. The next thing is on the we should not be losing click data, which by the way 3 and 4 are kind of similar. How do we take care of this? Is, let's say our Apache Flink service goes down, or any of so that means that it was in the middle of aggregating data on 31st second, it went down. Now there are different ways to do this. Your Kinesis or Kafka has a functionality called, rather, this thing. So we can increase the retention time in these streaming services, in these queues, and we can have the retention time of, let's say, 7 days. So even if at any point in time, we want to go back to the data and check for, retrieve any data, do some calculations again, we can do that with the help of this data retention policy. And if the aggregator goes down on the 31st second in the 60-minute window, there are two ways to handle this. One is that the aggregators have a functionality, a configuration which is known as checkpointing. What that means is that they can periodically checkpoint the state, their state to a storage device like, let's say, S3. So at 31st second, it checkpoints data that in S3, it checkpoints data in S3 that for the first 30 seconds, so many clicks for this particular ad ID, and when it goes down, when it comes back up, it can just retrieve data from the S3 this checkpoint and resume. So in this particular case, we do not do the work of 31 seconds, but because our time window is only 1 minute, we can get around that. We can let the data to be read again from our streams if required, and that will take care of it. However, this particular approach would have been used if we want to aggregate data over, let's say, an hour-long window or a day-long window. In that particular case, if the system goes down on 59th minute or 23rd hour, then we would not be doing the complete work again. We can just put data from the checkpoint and then start from where we left. So in this particular use case, we do not need to go for checkpointing. However, we can increase the retention policy, let's say, for 7 days, and that should take care of the fault tolerance already taken care of. We do not lose the click data. Now the other thing is data integrity, which is important here, and why it is important is that the click data is pretty important. If you think about the business model of Facebook, it runs on ads. There's no other way it can work. It can sustain the cost, and the way to make sure that, and hence that is the most important part of the business of the tech. So they would not want any incorrect data to be present in the system. So it is possible that at any point in time there might be a wrong code push in any of the aggregators, and we might be giving wrong data to the user, and this way they would be charging less or charging more. So we don't want that situation. What we can do in this particular case is we can go back to our previous solution, where we are also calculating the number of clicks through a batch job. So we have two different streams. One is real time, and then the other path is, let's say, more is less real time, but it makes sure that we are doing it. It acts as a kind of a test case for the data which we are capturing, aggregating, and providing to the user. How do we do this now? So this particular stream, whatever that stream is, allows a way to dump the data into any storage device. It could be again a database or S3. So let's do that. So we have a database here. This is our old Cassandra database. It writes to this particular database in parallel to putting data into Apache Flink, and then we will have the same thing. I was going to repeat the same thing. So Apache Spark. We have Apache Spark here, we have a cron job here. And then what we have here is a reconciliation service. So let's say after every 5 minutes, we have a Spark job which calculates data which aggregates data for over a 1 minute interval. Once we have the data, we will compare that with the data in OLAP database for that time interval. If there's a discrepancy, we will raise an alarm to the tech team, and then they can do two things. One, correct the data wherever the bug is, figure it out, and at the same time fix the bug. So in that situation, the data integrity is managed and maintained. Cool. So this also is done, and the last thing is data idempotency. Now what does data idempotency mean? So a user clicks multiple times in a couple of seconds, and the intention of the user was to click only once, but in haste or because of their behavior pattern or whatever, they clicked that ad multiple times. Now we want only one click to be captured instead of multiple clicks. One way to handle this is to have this thing, the user ID in that particular payload for click, and then we can dedupe the data in a specific time window before we put it on the stream, which that will obviously happen at the click service end. The problem with this approach is that we do not allow users who are not logged in to even view the ad, and which might not be the best solution, the best approach for a platform like Facebook. So we would want them to view the ads even if they are not logged in. So this solution cannot work. The other thing we can do is let's say, have some kind of you know, Redis kind of thing, where we capture from the user's end the IP, and if that particular IP is being for the same ad, it comes in a specific time window, then we dedupe it again. This system could work, but then the problem is, what if it happens uh, on the either side of the time window? So at 59 second I clicked the ad, and on first second I clicked the ad. Now there is no way to dedupe. Now I have two impressions of the same ad ID or the same click, though it should have been one impression. So this system also has some drawback. The other thing what we can do is, we can have a impression ID for each ad given here. So whenever I am serving an ad, my ad service will add an impression ID, which is something like a unique ID, a UUID, which would be given by the ad service, generated by ad service. And then so now that UID, that impression ID, is at the ad, and whenever I click the ad, with the click information, I also share the impression ID information, the UID information, and through this particular UID we can dedupe our ad, and this again would need to happen before we put the data on our AWS Kinesis. So I think I need to make sure, I'm sure my data idempotency solution is not picture perfect. I think some of the concepts are not clear in my head, and I need to go back to the system design by Hello Interview to figure out what exactly is the solution, what are the gaps which could be resolved. But more or less this has been resolved. We have completed our system design for Ad Click Aggregator, and in the future, in my next iteration, I will go back to data idempotency, and then we'll add the proper solution for this as well. So cool. I think that was it. Yeah, our Ad Click Aggregator service system design is complete, and I will pause the video here. Cool. Thanks.